All right, I think we are ready to start. It is my really big pleasure to be able to welcome Nobel laureates Gensel, and Parisi to Alba Nobel campus and this nice setting. We hope it's going to be a nice setting where we get to know the scientists beyond this amazing science. So my name is Ariel Gubar. I'm a professor at the physics department here at Stockholm University. I'm also a member of the Royal Swedish Academy of Sciences, which is actually the organizing body for this particular meeting. I was supposed to be here with my colleague Hans Hansson. Sadly, he is ill today, so I'll try to do my best to run this show on my own. So the program is that we will be having 3 30-minute presentations by the laureates, starting in chronological order. We'll start with the 2020 prize and 2021 laureate after, and then we will have a coffee break. And after the coffee break, I hope you will have many questions for the laureates to answer, and then we have half an hour, 3/4 of an hour session where you hopefully save your questions for the after coffee then. So again, as I said, today we want to learn more about the scientists and their journey to become very exciting, very leading scientists. And in order to refresh their memories, I also put some pictures of the laureates when they were a lot smaller. So hopefully they will take us from this picture to today. For Professor Gensel, I think you realize that he was a very mature child already. So, starting with the 2020 prize, some pictures are easier to find than others in the internet, I should say. So the 2020 prize, as you may recall, celebrated one of the most fantastic phenomena in nature, namely black holes. And half of the prize was given to Sir Roger Penrose for robustly showing that black holes, the creation of black holes, has to happen, is an unavoidable consequence of Einstein's theory of general relativity. Unfortunately, Professor Penrose could not be here today. However, the other half of the prize went to Reinhard Genzel and Andrea Ghez for their amazing work studying the orbits of stars around the center of the Milky Way to establish the nature of the invisible body at the very center of our galaxy, harboring 4 million times the mass of the sun. So first out then, we will have Professor Gensel telling us about his story, and he has been spearheading these amazing efforts of high spatial resolution imaging and spectroscopy using the telescopes in Chile belonging to European Southern Observatory. Sorry. So Professor Gensel, the floor is yours.
Thank you very much. So, I'm an experimental astrophysicist, so is Andrea, and we've been taking a longer trip. And I want to tell you a little bit about my side of the trip, a 40-year journey to follow up an issue which had come up 100 years early in Einstein's theory, was predicted to exist, but was fairly difficult to hunt down. And it did take us a long time, and as you will see, this has a lot to do with patience, with many young people, big telescopes, and going at it for a long period of time. These are the telescopes of ESO's very large telescope system up in Paranal in Chile, as you look at the Milky Way, and that's where we're doing our experiment. Now let me start, however, where I come from. I was born in a town called Bad Homburg, which is near Frankfurt. Frankfurt, of course, in the center of Germany. Then my parents moved when I was in 3rd grade to Freiburg, beautiful town in the Black Forest, where I went to gymnasium and my first university years. Then I went to Bonn, because in Bonn I could then join a new Max Planck Institute in radio astronomy, where I did my upper studies and also a PhD. From there on, this went automatic for reasons I don't understand. From there on, it went to the US. My wife, Orsha, and I already wanted for quite some period of time to move to the US, and so we got the opportunity to move to Harvard and join Jim Moran's group, who is sitting here, to do very long baseline interferometry and study with very high spatial resolution the skies. In a way, some of the work on the Galactic Center you can see already sort of simmering in the background. Then came the opportunity to come to Berkeley and work with a very famous physicist, and then finally back to Germany, to Munich. And now, as I get older, we also have a little house near the Alps, south of Munich. Mentors, very important. My father was such a mentor. He was a physicist. He was a solid-state physicist, experimentalist. I learned physics from him. A second mentor I had was Peter Metzger, director at the Max Planck Institute for Radio Astronomy. Then came Jim, whom I worked with and learned a lot from. And then, in a way, my second father was Charles Townes, the Nobel laureate for the invention of the maser and laser principle. And Townes had, I don't know why this is going automatically. What have you done to me? I assure you, I've not done this myself. Right, yeah, I will. So Townes had set up a experimental astrophysics group moving westward and doing astronomy to look at molecules, discover molecules. And he was fascinated by the idea that there might be a black hole in the galactic center, which had been predicted by theorists in the 1970s, Martin Rees and Lyndon Bell. And the galactic center, in a way, serves as a laboratory. It's the closest galaxy we have. Now, 40 years later, know so much more. We can put a universe into a computer and make very detailed simulations as the universe, like ours, expanded. Dark matter, which are these blue structures present, and form the structure of the forming system. And within these dark matter structures, this cosmic web, galaxies are beginning to form a few 100 million years to about a giga-year after the Big Bang. We can nowadays actually see these early structures, see the black holes which are forming in the centers of these galaxies, and see them grow. Dark matter brings baryonic materials into the centers, and when the galaxies and the central black holes grow a lot, well, then black holes can get nasty. They start accreting material and spewing out material again, jets and radiation, and they're beginning in the end to do harm to their galaxies. In fact, they can kill their own hometown galaxy at the very end, and many of the most massive galaxies probably end up in the cemetery of galaxies because the black holes got a little bit too active in their vicinity. So that's the big question which we would like to understand, and not only in the computer, we would like to understand them through detailed observation. Now, of course, this is going back in time. In astronomy, we can do that. We can go back in time because the speed of light is finite. And so as we look at very distant objects, we look also at the same time into the past. But we can also, with high-resolution techniques, hoping to get at the central regions and see how these galaxies operate, how they grow. All of this is nowadays possible, but it's not easy. And that's really part of the story for the young people here, that this wonderful explosion of wisdom and knowledge in our field has come, of course, because we have even at the radio. So you need to use all of these tools to understand and probe the evolution of these galaxies. So one of our instruments is a millimeter interferometer in the Alps. We've just built an upgrade of a integral field unit and adaptive optics imager on the VLT. And all of this serves to explore very fundamental questions like black holes, like the evolution of galaxies. Now, this has been a very, very exciting period of 40 years. We've learned so much about the galactic center, as you will hear from me and Andrea, but also about how stars form, about molecular gas in galaxies and other galaxies, how the activity of galaxies is controlled by various mechanisms, what powers star formation, how galaxies and their embedded black holes interact with each other, and this effect of feedback, which I already mentioned. And as we go on, we go back in time ever deeper. The James Webb Telescope is now beginning to explore the region of a few 100 million years after the Big Bang. And as you will see, a next big set of telescopes will come to explore that in even more detail. Now, this is our machine, the VLT, and we are using this, in fact, to get very high angular resolution observations, for instance, of the mass distribution. When we started 40 years ago, my God, this is running away from me. Jesus God. So when we started, we were basically far away from the center. Here's the center of the Milky Way, measuring the mass. And then both groups, over time, went further and further to the center to show that there is indeed a compact central mass of 4 million solar masses. We've been able in the last years to go ever deeper in, measure the motions of very fast-moving stars, see the effects of general relativity, and also, in fact, see the gas very, very close to the galactic center on the scale of a few times the event horizon. So we are pretty much convinced there's a black hole in the galactic center, but much more is to be done in the future. And this is our future machine. Andrea has one as well, the TMT. This is the ELT, European 40-meter telescope, which is being built right now in the Atacama Desert. $20 tons, 7 meters high, to do imaging and slit spectroscopy with this ELT. This machine, Mikado, is being built right now. We hope we might be able to put it on the telescope in a few years' time. Now, the pandemic, of course, has delayed things a little bit on the mountain, but we are on a good track. This is, of course, a pan-European type collaboration where several countries participate in with several research institutions. And the gain in the angular resolution of this machine is enormous, factor of 10 almost, and also the sensitivity. The Webb telescope is extremely sensitive in the infrared. This one will be as sensitive, but has the additional element of tremendously high angular resolution, so we can look into the centers of galaxies, resolve what we couldn't resolve before. So that's the current view. That's what we hope to see. Go very, very close to the black hole. And as we go back in time, look at the first black holes and how they formed. There's the machine right now. The dome is being built. I apologize. As we know, the time is moving faster away from black holes. So thank you very much.
Thank you very, very much. Next, we welcome Professor Anja Guess from UCLA. She has been monitoring the same stars in the galactic center. Yeah, but using the Keck telescopes in Hawaii, and in particular, pushing the frontiers of laser-guided adaptive optics. So we are really excited to hear your story.
All right, let's see if we can get this projected. And at what speed my presentation will go.
It'll be speed of light.
All right. All right, so my interpretation of this seminar was slightly different. So I understood that we were going to share our experiences of being young and aspiring physicists. We were asked to think about how we oriented ourselves in the diverse landscape of physics research and what important decisions we made in our research careers and how today we view the future of our own research. So I'm going to start earlier and try, for the sake of the students in the audience, to share my path. And these paths are often nonlinear. There's lots of bumps and starts. So for projects that seem so clear-cut and perhaps obvious at the end of the day, the paths to get there are often not. I also think this question of how we make our decisions is a particularly interesting one, because I think it's a combination of our own individual passions, the institutions and families that we come from, as well as the context, where the field is, which is constantly evolving. So you can start these stories at various points in your own professional development. So I decided to think about when I actually considered myself to be a physicist. At what point do I really consider the beginning of my professional career? And I would orient that as an undergraduate student at the Massachusetts Institute of Technology. It's when I had to declare my major, and I was very excited to be majoring in physics at the time. And this is a university that's strongly committed to undergraduate education, especially in the research world. I think 75% of all the students there are involved in research before they graduate. And today, that's really influenced my own thinking about the importance of involving undergraduates in my own research program, because I'm so grateful for the early opportunities I got here, especially under the mentorship of Professor Hale Brock, who really made a world of difference in introducing this world of astrophysics. MIT at the time was very strong and continues to be in the world of high energy astrophysics. So as an undergraduate, I thought black holes were cool. How can you not? They're really intriguing objects. They defy our understanding. They represent in so many ways the frontier of our understanding. In high-energy astrophysics at the time, the focus was on stellar mass black holes. So the first kind of black holes that we understood to be out there, the ones that are the outcomes of stellar evolution, the most massive stars in our galaxy. But these studies were done with X-ray satellites. MIT is really famous for these, and I was hired to program for an onboard data acquisition system, and I learned to code, and I thought this was so cool. I also got the experience of being introduced to MIT's telescopes, so the world of ground-based astronomy, where the objective was to identify the optical counterparts of these X-ray sources. And I thought this was a fascinating world. I thought it was exciting. I thought there was a lot more to be done in the world of high-energy astrophysics. But at the same time, the people I was working with were advising me that this is a field that had had a huge infusion and that there was likely to be a big lull coming up. And so I paid a lot of attention to that. So as I went to the next institution for graduate school, which is I went to the other coast, California Institute of Technology, so from one tech school to the other, I chose Caltech because it has fabulous instruments. Some of the largest telescopes in the world are run by Caltech, and it struck me that these what you want as a researcher is to have access to the best tools in the world. Because I had already come from a world of high-energy astrophysics, I entered a group that was about high-energy astrophysics. It was actually balloon-based experiments where they were developing new techniques to understand these high-energy gamma rays. And I really enjoy methodology, coding, and that's going to be a theme throughout, that is a theme throughout my career. After the first year, I learned of a new project that was opening up at Caltech, and it was about using new techniques to use their large ground-based telescopes. This is actually me in grad school, young and naive, but very excited to be at Palomar, which at the time was the largest telescope available at these wavelengths. And there was a project that the guy I was working with at the time, Tom Prince, had just joined. And it was a fascinating project in a number of ways. One, it was a collaboration amongst 5 Caltech professors, which is a remarkable thing in itself. There were only 2 graduate students on this project, so it was also interesting from a sociological perspective. I learned a lot. And it was to use optical detectors to try this technique called speckle imaging. So speckle imaging is a technique where you take very short exposures to compensate for the blurring effects of the Earth's atmosphere. It turns out that the turbulence in the Earth's atmosphere is far more severe at shorter wavelengths than longer wavelengths. So the work that Reinhardt and I have both done is all in the infrared. So you might be asking, why was the proposal in the optical to begin with? And the answer is the infrared detectors simply weren't there in early graduate school to do this kind of work. So it was an exciting project. The promise was to be able to discover supermassive black holes at the heart of active galactic nuclei. So again, I thought, black holes, pretty cool, let's do this. And very quickly it became clear that in this proposal that had been written, this was back in 1987, had overpromised what this technique could do. And I think this is one of the interesting junctures. Actually, we've kind of passed a couple of interesting junctures in terms of decision making. The first decision you always make in graduate school is who you work with, and that matters a lot. I mean, it matters not only in terms of the projects that you work on, but it also, different mentors have different styles. It's almost like a form of dating. You have to find somebody who's a good match. With 5 professors on this project, there were a lot of choices. I was really grateful to end up working with Professor Gary Neugebauer, who was a great mentor, and really had the vision that this technique would ultimately be possible at infrared wavelengths. But in the meantime, at optical wavelengths, I was really forced to make a decision. Was I going to stick with the technique or stick with the science? And as a graduate student, I decided to stick with the technique under the belief that new technologies would open up new arenas. So even though the original science that I was interested in, finding supermassive black holes, the technique could answer different questions. And so the question that I got interested in as a graduate student was to understand star formation. How are stars like our own form, and under what conditions might they form planetary systems? And I started studying star birth and discovered that most, if not all, stars form as binaries. And I raise this because you'll see how this comes back in my research evolution. So while it felt like a left-hand turn and going into an arena that had nothing to do with the long-term journey, it actually greatly informed the project that followed. At the end of my graduate career, Keck was just coming online. So the Keck Observatory is the largest telescope in the world today. It's a 10-meter telescope. It's run, co-owned by the University of California and Caltech. So as a young Caltech grad student, I saw the very first images from this telescope as I was graduating. And it was clear to me at that moment that what I wanted more than anything else was to get a job within that system. And it quickly became clear that UCLA was a really exciting place to work because they had decided to develop a program, a set of faculty devoted to the development of infrared astronomy and astrophysics. So today, as I said at the high school this morning, I feel like I have my dream job. It's a wonderful place to work. Not only because I have access to these telescopes, but because I have remarkable colleagues who I really want to give a huge amount of credit to today. So while the Nobel Prize tends to recognize few, as Reinhardt already demonstrated, behind these programs, or with these programs, are a huge number of people. Actually, let me just skip forward to share those people. So when I first came to UCLA, the folks that I began collaborating with right away are Mark Morris and Eric Becklin, who are here. So Mark is right here in the front row, and Eric is in the back. I've had the tremendous pleasure of collaborating with these two for 30 years, which is also a rarity in science. And I think the choices that we make, some of the most important choices that we make, are not only who our advisors are, but later in life who our collaborators are. Our collaborators enrich and I think facilitate really challenging programs. This program was challenging in ways that I hadn't anticipated. So while I was delighted to get a job at UCLA, I was interested in developing the ability to do speckle imaging at Keck. So taking what we had already done at Palomar and applying it to this new Keck telescope. Our very first proposal was actually turned down. It was turned down because people didn't believe that the technique would work on a segmented telescope. So Keck is 10 meters in diameter, so like the width of a tennis court. But rather than being a single mirror, it's composed of 36 hexagonal segments, each of which have to be aligned to a fraction of the wavelength that you're observing at. So this was a radical new idea in telescope design. No experiment to that point had actually required that the telescope be fully phased. So there was a lot of skepticism about whether or not it would work. I'm very fortunate in the sense that while the first proposal was turned down, there are colleagues who lent me telescope time, which I don't know, you can't really pay them back. It's one of our most precious commodities as researchers, is actually access to this facility. The typical astronomer or astrophysicist within the University of California gets 2 nights every 6 months. So a few hours is actually a precious commodity. Nonetheless, we were able to demonstrate that this technology would work and that we were in a position to ask the question that we set out to answer. Is there a supermassive black hole at the center of the galaxy? This is, of course, a fundamental question to prove that these supermassive black holes really do exist. And of course, our galaxy is the best place to study them. It's the closest example of a supermassive black hole that we'll ever have to study. Now, I do want to give full credit to the larger team. So while we started out as a team of 3, I should have mentioned, on the right is my very first graduate student, Beth Klein. Today we're a much larger group, and the people that I want to highlight who are here today, I know he's in here somewhere, Tuan Do, who started off as a graduate student in the group and who's now a professor in his own right. On the left of the screen, who couldn't make it, here is Jessica Liu, who's up at Berkeley today. And then another scientist who's been with the group for the last decade is Shoko Sakai, who's also here somewhere. There's Shoko. So we have an amazing team. We have a core collaboration of about 24 people and a broader network of collaborators of about 100. And as a group that started as the little engine that could, we've become, I think, what you call a key science case for the development of technology, both on Keck and, as you'll see, the future 30-meter telescope. All right, so our journey was all about finding these supermassive black holes. Now, I want to make sure that you guys are just as skeptical as the high school students that we talked to this morning are. The proof of a black hole is the demonstration that there's a tremendous amount of mass inside a small volume. In fact, I emphasized this morning, the citation says, we didn't discover a supermassive black hole. We discovered a supermassive compact object. And so I think what that really signifies is that while we've moved the case for a supermassive black hole from a possibility to what I would call a certainty, it's still allowing some wiggle room, and that's because we have not confined the mass to within its Schwarzschild radius. So it's confined to a volume that's a factor of 10 million times smaller, but nonetheless is not within the Schwarzschild radius. I thought I could subtly skip over this, but Emily's going to show you all the things I'm skipping over. Okay, so we're looking at the center of the galaxy. So if we live within our own galaxy, which is a flattened disk-like structure, you see all the stars in this wonderful picture from the plank of Hawaii. And it nicely demonstrates one of the other challenges we face in studying the center of the galaxy. So in the center of the galaxy, or towards the center of the galaxy, we have to look through a tremendous amount of dust. Dust absorbs optical wavelengths very well, but infrared wavelengths can penetrate through this huge amount of dust. In the early 90s, the infrared and detectors had also reached the point where you could finally do these high-resolution imaging techniques at the center of the galaxy. So it's useful to keep in mind that there are actually 3 things from a technological perspective that are coming together or converging in the late 80s, early 90s to enable this experiment, an experiment that could not have technologically happened before. So just to name them, they're the development or the infrared detectors becoming low enough noise to see the stars at the center of the galaxy, to have the telescopes that are large enough to see these individual stars that are so close that their individual orbits can tell you the mass that's inside their orbit, and that those orbits are small enough that you're close enough to the Schwarzschild radius to convince yourself that you have a supermassive black hole. Now, as Reinhard has already said, one of the issues here is the atmosphere. So you have to overcome the distorting effects of the Earth's atmosphere. In the early days, this was done with speckle imaging. So very software intensive, hardware simple. Inexpensive. So it only required modifying existing instrumentation in terms of the pixel scale, so that you could actually capture the highest resolution information that's contained in these images, and then changing the electronics so that you can keep up with the distortions in the Earth's atmosphere. So you need to take pictures roughly 100 to 1,000 times a second. Today we use much more advanced techniques of adaptive optics, and here you might say it's hardware sophisticated, software simple, but it's hardware sophisticated, software complex. You never left the software complexity. And here with adaptive optics, you do basically a factor of 10 better than in any way you can describe an image. So you see the images, you see stars that are fainter, you can position these stars more accurately. But with all of this, the time baseline is essential for measuring the orbits. So today I'm just zooming into the central region, which is a fourth of the real estate of that little inset. You can probably find my favorite star in the universe. Its name is SO2. It's the most powerful star today because it's the star for which we have complete knowledge of the orbit. It's going all the way around, and we've been able to measure it both in imaging, which captures the motion in the plane of the sky, as well as spectroscopy, which captures the motion along the line of sight. The way this is coded is that once a star is detected with images, it's trailed by a dashed line. And some stars appear not because they're variable, but because the technology is allowing you to see deeper into the field. And then once you can finally get the spectra, which are so valuable, not only in terms of being able to see the motion along the line of sight, but understanding what these stars are, that they're not just the canonical test particle that we learn about in first-year physics. Okay, so SO2 goes around in every 16 years, and that's the star that has taught us that there's 4 million times the mass of the sun, which we knew about from Charlie Towns's early work, inside an enormous region that was much, much larger than the Schwarzschild radius. So in fact, if you read those early papers, it's only a suggestion way inside the paper that there could be a supermassive black hole because you're so far out from the Schwarzschild radius. And what these experiments have done today has been to confine that mass to a volume that's a factor of 10 million times smaller, advancing the evidence for the existence of a supermassive black hole. So today, in spite of the citation, I'm going to make the statement, we have the strongest evidence today for the existence of a supermassive black hole, not only in our galaxy, but in any galaxy out there, and it's in our very own backyard. And this is providing us in our own galaxy with a wonderful laboratory for understanding both the physics and astrophysics of black holes. This is an animation that I think is one of my favorites that's come out of this work. It's a collaboration with the University of Illinois' Advanced Visualization Lab to capture all the surprising science that's come out of these measurements of stellar orbits. So while we've been able to answer the first question of is there a supermassive black hole, this new technology has actually unveiled more questions than answers. We've discovered young stars where we expect none. We see few old stars where we expect many. And we see stars that we didn't even think to make predictions for. For me, I used to joke this is like job security, or it's like being a kid in a candy shop. There's so much more to do. Time helps you in this business of orbit measurement, but also technology helps you a tremendous amount. There are many ways to advance technology, but in the ways that we're pressing forward, is to advance your adaptive optics. Today we use a single laser to correct for the distorting effects of the Earth's atmosphere. That actually corrects roughly 30% of the problem that exists. You can make more progress with today's telescope by launching multiple lasers. It's basically doing a CAT scan on the atmosphere so that you capture the full all the scales of distortion that are out there. Actually, all the layers of distortion that are out there. And in fact, what you miss becomes more problematic as you go to larger and larger telescopes. In other words, the future of these big telescopes, which you've already heard from Reinhard, so we have our own little short video of the next generation of technology with these big telescopes. So we're moving from a 10-meter class telescope to a 30-meter class telescope. In the world today, there are 3 such programs under construction. The project that the University of California is part of is called the 30-meter telescope. It's planned to be in Hawaii. And there's all sorts of interesting technological challenges associated with this facility. Some of my favorites include, this is going to be the largest moving structure ever built on this planet. So the people who build domes, astrodomes for stadiums are actually the ones who are thinking about this. And one of the big issues is how do you prevent weather inside your dome? Another interesting choice, technical choice associated with these facilities is what is the size of your segment? So remember Keck is 36 segments. So you might think that you would go the same size or bigger because you're working with a bigger telescope. But in fact, the choice was to go smaller, to go to 0.5 meter. And again, it's all about several technical issues, but one of which is how do you achieve the shape of the mirror to have the cleanest approximation of a parabola? How do you have those segments sensing each other? And what might seem trivial, but is actually not trivial, how do you clean the thing? All right, so today, this shows an animation from the left of where we are today with today's technology to today's telescope, tomorrow's adaptive optics, and then on the right is the next generation of both telescope and adaptive optics technology. You can see, hopefully, that today we're only seeing the tip of the iceberg. So while we're seeing a population of stars that looks nothing like what we predicted, perhaps some of the solution is that we're only seeing the brightest, the oddballs. And maybe an analogy would be with the financial market. It would be like trying to understand our economy if we only looked at the largest transaction, which are the rare events, and without being able to see the much more common but fainter things. That is true in the stellar world. So today, we cannot see a star like our sun, which is a common star at the center of the galaxy, simply because we don't have the resolution. So this is what we think the future holds. And to do this work, I'm pleased to say we've trained many students over the years because it's clearly going to be their futures that are going to unravel all the questions and opportunities that come out of this work. And let me just end by saying not only do your scientific collaborators matter, but your funding partners matter tremendously. So thank you for your time.
Thank you very, very much. Let's see, so, my surprise, we're ahead of schedule, which is good. There will be lots of time for questions. But now we will be moving on to the 2021 prize, which was given for groundbreaking contributions to the understanding of complex physical systems. And it was again shared into two halves. One of them was given to Professors Manabi and Hasselman for the physical modeling of climate, and sadly none of them could be here today. But we're extremely pleased to have Professor Laureates from Rome, where his share of the prize, the description was for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. And I guess it's the latter part that is worth emphasizing. The range of scales that Professor Parisi has been working on, and in addition to that has been working on, in addition to the glasses systems where the prize was meant, or originally the prize, he has been making enormous contributions to hadron physics and mathematics, quantization, novel quantization methods, and so on. So it's an enormous honor to have you here today, and we're looking forward to hear about your path. And I guess you will not be showing slides, which means you probably should make the room brighter, right?
Yes.
Yeah, let's see if we can do that.
Okay. Thank you so much. Thank you for the wonderful presentation. And I will try to describe somewhat my path he's asked me to do to the Nobel Prize. And have you seen that there was a nice photograph of me when I was a child? I think that was I was in the second year of primary school, or the first year, it's difficult to know. At that time, one had here where you see a hole here where you have the ink because we have to use some pen taking the ink and so on. And I think that when I was 9 years, my parents gave me a stilograph where I could use right without having to take ink from there. Anyhow, at the time I was told by my mother, I mean I don't have so many recollections at the time, but was told by my mother that I have a very interest in mathematics, and I remember that I was reading astronomy for children, I mean things for children of astronomy, but my teacher at the elementary school were surprised, at the primary school were surprised that they knew the name of the planet, the dimensions of the planet, and things like that. And my father wanted me to be an engineer. I have an aunt who was thinking me like a Newfoundland, but at the end, when I was in high school, I was not really thinking what I should do when I was going to university. It was more or less decided that I should be in engineering, but I was not thinking about. And when I really to go to university at the age of 18, I mean, I liked at the time, I liked lots of mathematics. I started to study some mathematics beyond the program at high school, but I was studying not in a professional way. I mean, I was reading books based on mathematics, I was looking things on encyclopedia, I looked into derivative, integral, some analysis of the type. And when at that moment when I was saying that I had to go to university, I had to decide where to go. It was quite simple for me to decide that I don't want to become an engineering, especially because in my mind, also in the mind of my parents, an engineering is someone that builds houses. There was no idea that my family that you could be an electronic engineering, or you can have airplane engineering and so on. Engineering is someone that builds house. So I decided not engineering. I was good in mathematics. And for the only possibility were at that moment mathematics and or physics. Now, the point is that the mathematical history books were ending with the end of 19th century, and 20th century mathematics was never told. And we know because 20th century mathematics is a much more abstract. It's not easy to write a popularization book of about last century mathematics. But on the other hand, there were books of physics in which physics was described. There was physics, a lot of physics was described. The discovery of quantum mechanics, the discovery of atomic reaction, of course the atomic bomb, nuclear power and so on. We had all the history of Fermi that was, as you know, was in Italian, was working at my university, and therefore there was a narrative gap between 19th century and 20th century mathematics on what was doing. I think that at the moment where I have to decide to do mathematics or to do physics, just because I had information what was physics at that moment, but did not have the information what mathematics was at the time, I decided to start to do physics. I was interested in mathematics. I always been had more knowledge in mathematics or typical theoretical physics of my generation, but I started to do physics, and now physics in Italy. At that time was organized that people go to university typically in age of 19 years. I was in 1 year in advance, I went to 18. Anyhow, the typical course is 4 years in physics. However, many people take a little more time to write the thesis. And the thesis at the 4 year at the lower level was, and is still nowadays in the 5 years, a research thesis. So you do research thesis at the level of the first, the only one course, because at that time there was no PhD. I mean, PhD were introduced in 82, 83. So I mean, at that time there was no PhD. So I started to do the course. After the first year, I started to study a lot of things by myself. Because the first year I was intimidated by the courses, and I tried to prepare my course as my exam at the best. After that, I got a very good, the maximum grade for the first year. I realized that I could try to look also to something extracurricular things, and I was reading a lot of books. I think that there was one of the books that things that was very useful to me was the Landau series, the series book of Landau Elliptics. And the thing that was very, very strange in Italy, that of course I cannot read and was not able to read Russian. But in principle, you could read in English, but they were very expensive. Of course, I could afford English. I could afford to pay them, but they were translated into French, and at a price that was 10 times smaller than the English edition, because they were published by some publishing house connected to the Communist Party. So there was a lot of things. So there was the mere editions. I don't know why there was important. There was this edition of books that was connected to the Communist Party that had a lot of, not only Landau literature, but also Confiaghi and people mathematics, fun books on differential equations, so on. And in this way I also learned French, because the books were in French, but the formula were in universal language. And okay, so I studied school, I studied university, and after the third year, I have to decide what to do at the thesis. And where in my university at the time, between the students of the time, there was a very clear categorization. High energy physics, particle physics was the most interesting physics. Once I established these things, theoretical physics was better, definitely better than experimental physicists. And among the theoretical physics that were at Rome at the time, there was Nicola Capito, which was by far considered and was correct the best physicist in there. So, so I tried. So when I asked, so therefore I decided to ask the thesis with Nicola Capito. Nicola Capito accepted me. It was not easy because he was taking only one student per year. But I mean, he said yes without making many inquiries. And after some time I was asking, but what should I do for thesis? They say, well, I don't have a precise idea. Why you don't find something? And at the end, there was also a very nice physicist, theoretical physicist. There was a theoretical physicist at that moment in Italy was wonderful. There was Gianni Iona, which also came here to take the Nobel Prize from Nambo, because Nambo was unable to come here. And Gianni Iona suggested me to do a thesis on something connected to the broad angular Higgs mechanism. And there was one problem to understand if it was correct that there were no particles that was remaining. There was a computation that was done by Polyakov and Mittal and published on the Russian GPT, translated into the books were usually translated at that time. And I mean the review, and I did this thesis, and okay, it was just a standard computation, I did this thesis. After that, I get a fellowship to go to Frascati. Frascati is a very important center just near Rome, but it was a high energy physics experimental center, but there was also a theoretical group. And the point was a place was extremely important at that moment. It's still important, but there the reason was the following. It was an experimental group which people started there with an electrosynchrotron. And after a few years, there was the electrosynchrotron was a brilliant physicist, Austrian physicist that was in Rome, Bruno Duszek. And Bruno Duszek had a wonderful idea that you can make an electron-positron collisions. That you can use the same rule to make a collision between electron and positron. And the way that Duszek was arguing that was very compact. He said, you know, there is a PC theorem, and the PC, I mean, electrodynamics is invariant parity and just conjugation. So if you put an electric and magnetic field, the electron and the positron will stay on the same orbit, but going in the other direction. So he was a theoretician, but he started to study also how to construct. There was a group that formed quite fast, and at the end the machine was working. At that time, it was the unique practical. There was the biggest machine for electron-positron interaction, and it was a machine that was able, and indeed, have seen the J-psi resonance, but the J-psi resonance had been seen just too late, because in principle, too late, it was 1 week later than the Americans. The reason was the following: that the machine has a nominal energy of 3 GeV. The resonance was 3.1. Now stretch using the machine a little outside what is supposed to increase by a little the current, you can go to 3.1. Then he said, no, it will not break if you increase the current, but normal operation was not going. Anyhow, at that point, there was electron, everything was, people were interested in scaling, in deep and elastic scaling, and hadron production is plus and minus. It was a moment where Feynman invented the idea of partons. Partons were something like a constituent of the hadrons, but it was not clear if the partons were quarks, were gluons, or there were other things like some kind of nucleon, mesons, and so on. So I was so interested in this problem of energy physics, and I started to concentrate my understanding on deep analysis scattering and plus or minus collision interaction of electrons, of particles at very high energy. Now, I think that was quite particular that was something important detour from this type of parts, was that a very good friend of mine, Marco Deram and Luca Pellitti, that were doing a thesis in not in high-energy physics. They also asked to Cattipo, but Cattipo said no, because they had already been. But they were asked to Gianni and Carlo Di Castro. They were doing a thesis with Gianni and Carlo Di Castro on statistical mechanics and on second-order factorization. Now, Di Castro and Iona had a very nice idea to use the renormalization group for to study second-order factorization, something that was done also by Wilson, but the way that Wilson was using the normalization group was very imaginative and was using it in a different way, in such a way that it was also a constructive way to use. And now, just because they were a friend of mine, I started to try to understand what they were doing, and I realized that the type of problem there were in the renormalization group in statistical mechanics in second-order factorization were similar to the problems that one has somewhere in normalization group in high energy physics, because the normalization group technique was started for high energy physics. And now that was that I started. I remember there was a famous book of Bjork and Drell that was ending with a discussion of a normalization group in quantum electrodynamics, and the discussion at the end was saying something that the result they can get some result that they had the impression that the result of the normalization group was crazy. And they said, look, everything that comes from the normalization group, but although that you must be very, very careful. Anyhow, the things was very interesting, and they start also to work on second order phase transition. And the point was that moment is something that was very interesting, because it was what people later on called cross-fertilizations. Therefore, there were a lot of methods, ideas that were coming from high energy physics and were going to statistical mechanics. And sometimes these ideas from statistical mechanics change again and were going back to high energy physics. And this is something that happened, for example, for the normalization, for the point of view of normalization group. The normalization group in Bjork and Drell was used just a tool to compute the next order log computation, electrodynamics, but on the other hand, when you went to statistical mechanics, it got the idea of fixed point. The idea of fixed point came back to energy physics to study the normalization group and so on. So I started to move also in my time, and also the things that was typical things that was going on. Also, for example, you have a Monte Carlo method that were invented for doing statistical mechanics, and they went back after to study lattice case theory, their fundamentals to understand quantum field theory. So I started to move from one direction to direction, oscillating a lot, but I think that apart from most of my interest was high energy physics, I had a first intermediate on statistical mechanics for phase transition, but was an intermediate of 1 year, and after I came back to do high energy physics. I was in Paris for 2 years. I was working there most energy physics. And when I turned back from Paris in 1978, I thought that was going on high energy physics. I was very interested to understand the QCD. And of course, at that moment, QCD, there were very little computation, because you can do the only type of computation that you can do was lattice QCD, but was not in the physical regime, was in the region of small betas. So there was an high temperature expansion, and I was trying to do some high temperature expansion. We wrote a paper with Duke and Sulas on high temperature expansion. And after we want to understand better these things, and just to try to understand better these things, I arrived to look into some, there was the techniques that were using to have some diagrams that were looking like polymer and so on. Therefore, these polymers were touching themselves, there was some repulsion and so on. So we want to understand better the theory of this polymer. And arrived to a paper that was on the theory, field theory of branched polymer, statistical mechanics of branched polymer, and the things that was written in the paper, that was there was the replica method that was applied for spin glasses, and then however it gave wrong result in the case of spin glasses. They were using it for glass polymer, but there was a note occasion that it should not, that for spin glasses get the wrong result. Well, at this moment I started to be more to understand why, because of two reasons. First of all, I did not want to use the method that sometimes gives the right result, sometimes gives the wrong result. And the second thing, I was thinking that it was a shame that we have a method that we don't know why it gives the wrong result, and so it's something that should be fixed. And at the beginning I was very bold because I was thinking that I could fix the things in 15 days because I think that was something like a clear mistake. In reality it was not a clear mistake, but at the end of a lot of work I was able to fix the problem, and therefore the problem was there was a model that was called the Cheriton-Kirkpatrick model of spin glass, that was the mean field theory for spin glass, and then finally I was able to solve the model and write down the solution. The solution involves, however, that was a quite strange things involved some mathematics that does not make sense in the intermediate step. I mean, the point is essentially the following. I think that everybody knows how to compute here an integral in one dimension, or in two dimension, three dimension, but it's not clear how to do the computation integral in half a dimension or in one-third of dimension. And you know the permutation group of two objects or three objects, but the permutation group of half object is something that is not well defined from mathematics, so the type of computation that I was using were using this type of concept, self-concept if you want, because they are not defined mathematically, so you cannot really say that they are concepts. But anyhow, the formula were, the final formula were fully consistent with mathematics, and the things that happened to me that I wrote the formula, there was some agreement, the general agreement that the formula could be right because they were consistent. They were also in agreement with a numerical simulation and so on, but it was not clear at all the meaning of the formula. However, having solved this problem, I came back to high energy physics because I was very interested to try to develop lattice, what people call a Monte Carlo method for lattice case theory. So I wanted to understand how one could do Monte Carlo for this type of problem and so on. Started to do numerical simulation in different models, and I left these things apart. After that, I went to high energy physics, and after I came back to the issues, and what happened to me that I started to do to work with other people on the subject, and using other people idea and also my own, we arrived to prove that the thing that was happening, that the system was a really complex system. I cannot spend too much time here because you want to know my facts. However, this was extremely important to resolve. The system was complex, a system that has many equilibrium states, and was some kind of, while the idea of complexity was something that was floating around in many different disciplines, it was a real surprise that the system was a complex one. So I found in my hands the fact that we have discovered that the mathematics of a complex system, the first type of complex system in physics that was not supposed at the beginning. So this means that I start to be interested in understanding better understanding better the theory, understanding better the theory of complex systems, and try to see if this type of ideas that were developed in spin glasses could be used in other ideas for like optimization and other type of algorithmic optimization and so on. However, at that moment I was very busy also with high energy physics, because we had a huge program in Rome on which I was the scientific leader. The scientific leader in reality was Nicola, but Nicola was busy also as Nicola Capipo, I meant, was busy as president of the Italian National Institute of Physics, so the head of the collaboration was myself, and the collaboration was an important collaboration because we were building a computer to do lattice-scale theory. It was a supercomputer which I think that for a few months was the fastest one in the world, but only for a few months. It was something that does not make too much sense to mention. It was a 1 gigaflop that can do 10 to the 9 operation per second with a memory of 1 gigabyte. Of course, 1 gigabyte nowadays is something like that, but 1 gigabyte memory at the time was something important. So after that, at that moment in the 90s, I decided, I left more like I finished doing this type of computation, and I went back to do high energy physics, to do statistical mechanics. And from that time, I've been working mostly of the time on things related to complex systems, to glassy system, real space-to-spin glass, to real glass window glasses, and to optimization, and to other types of statistical mechanics. So in some sense, if you want to, if you see my trajectory, the trajectory is something strange, because I started to be interested to things like statistical mechanics just by chance, because my good friends were doing a thesis on statistical mechanics. I started to be interested on spin glass, just because there was a paper that was saying that there was a mistake over there, and it was not known. In reality, the amazing thing is that the reason that why it was not working at that time was known, because there was published the paper of Towles Anderson, of Dr. Meda Towles, and however, it was not written there, so my interest was aroused by something that was not really interesting. But I would say that one of the things for which I feel that I've been very lucky. I've been very lucky because I arrived at the right problem at the right moment. I mean, at the moment in which there was the possibility of doing something useful. For example, one of the things that was mentioned in the Nobel Prize motivation, that was the planetary. Now, the planetary, it was something that was something that also this was something like a luck, because Roberto Benzi, a physicist, told me, look, let's go to see a seminar of Alfonso Sutera on glaciation. I had no interest on glaciation, but a friend of mine was said that the seminar was nice, and after the seminar we started to have some discussion with them to improve the idea of Alfonso in a different way, and that finally was a paper on stochastical resonance, and the paper of stochastical resonance is some paper of glaciation, so this makes the glaciation part of the stuff. And therefore, I have also some other important progress. For example, multifractality and turbulence happened because I was just in a seminar with Uriel Fritsch. Uriel Fritsch said something about experimental data, and after we had a long 2-day discussion with Uriel Fritsch, and we wrote a paper on multifractality. So the thing that happened, many things happen by chance. That, of course, it's clear that you must have the capability of solving the problem, not only see the problem, but to solve. But if you don't see the problem, it's clear you cannot do so much. And I think the other thing that I would like to say that thinking back to the time that I started with the present time, I think that the present times, the thing that I would like to say is that maybe the amount of things that you have to know to start to work in one field is much higher than in the past. I mean, this is quite clear because theoretical physics from my age have been working for 50 years. So the amount of accumulated knowledge in one field is much higher. Of course, there are new fields in which there's not so much accumulated knowledge, but if you have to start with nowadays it's clear that just because there is lot of accumulated knowledge, maybe it's more difficult to move between different subjects or different regions of theoretical physics. At that time was easier, and I believe that it's much difficult. For example, if you want to understand string theory, it will take lots of mathematics in order to arrive, study mathematics in order to be able to really hard mathematics in order to do so. Okay, I think that my time is over, so thank you very much.
Thank you very much for this amazing story, taking us through many diverse fields. So.